In 2001, a British science fiction writer did something unusual. He published a paper in the Journal of the British Interplanetary Society, which is a real academic journal and has been since 1933. And in that paper, he proposed that the night sky is fake, not metaphorically fake, not we're misinterpreting the data fake, physically, technologically, deliberately fake. Stephen Baxter argued that an advanced civilization, one commanding the energy output of an entire galaxy, could construct a kind of dome around humanity. Not a physical dome, something more like a projection system, a planetarium built at a scale so vast that every star you have ever seen, every galaxy the Hubble telescope has ever photographed, every cosmic ray that has ever struck a detector on Earth could be artificial, manufactured signals pumped into our solar system to create the illusion that the universe is empty. Baxter did the math. He calculated the energy required, the information density needed, the computational limits imposed by thermodynamics. And what he found was disturbing. A civilization operating at what physicists call type 3 on the Kardashev scale, roughly 4 times 10 to the 37 watts of continuous power, which is the total energy output of a galaxy like the Milky Way, could maintain this illusion for our current civilization. Every telescope, every satellite, every detector we have built or could build in the near future would be fooled. The sky would look exactly as it looks right now, silent, empty, vast and dead. But here is the part that turns a strange idea into something genuinely unsettling. Baxter also calculated when the illusion would break. If humanity ever expanded to span roughly 100 light years, the computational and energy demands of maintaining the fake sky would exceed even the capabilities of a galaxy-powered civilization. The dome would crack. We would see the real universe behind it. And whatever is out there, whatever has been hidden from us, would be revealed. The question this video is going to try to answer is not whether the Planetarium Hypothesis is true. Nobody knows that. The question is whether we could ever tell the difference if reality were lying to us systematically about the contents of the sky. Is there any observation we could make, any experiment we could run, any anomaly we could detect that would let us catch the lie? And what does it mean that the answer to that question is becoming, decade by decade, less obviously no? To understand why anyone would take this idea seriously, even provisionally, even as a thought experiment worth publishing in a peer-reviewed journal, you need to understand the problem it was invented to solve. And that problem started with a question asked over lunch in the summer of 1950 by a man who had helped build the atomic bomb and who would be dead within 4 years. Enrico Fermi was, by the accounts of everyone who worked with him, the most complete physicist of the 20th century. Not the most brilliant. That title probably belongs to people like Dirac or Feynman or Witten, but the most complete. He could do theory at a level that won him the Nobel Prize, and he could build experimental apparatus with his own hands and make it work on the first try. His colleagues at the University of Rome called him the Pope because he was never wrong. That nickname was not entirely affectionate. It is unnerving to work alongside someone who is never wrong. What most people do not know about Fermi is that his older brother Giulio was his closest companion as a boy. The two built electric motors together. They were inseparable, In January 1915, Giulio went in for routine surgery on a throat abscess. He was 15 years old. He bled out on the operating table. Enrico was 14. He walked past the hospital every day for weeks until the grief became something he could carry rather than something that carried him. His mother found him a physics textbook, 50 years old and dense with equations, and the grieving boy devoured it. He would later name his own son Giulio, born in 1936, after the brother he lost. By 17, Fermi's entrance exam essay for the Scuola Normale Superiore in Pisa was judged to be doctoral thesis quality. He had his PhD by 21. He was the youngest physics professor in Italy by 26. He married Laura Capon, the daughter of a Jewish Italian Navy admiral, in 1928, when Mussolini's racial laws began targeting Jewish families. A decade later, the Fermis needed an escape route. The Nobel Prize, awarded to Enrico on December 10, 1938, was their ticket. They traveled to Stockholm for the ceremony and never returned to Italy. They sailed directly to New York. On December 2, 1942, underneath the squash courts at the University of Chicago's Stagg Field, Fermi achieved the first self-sustaining nuclear chain reaction. They celebrated with a single bottle of Chianti and paper cups. At the Trinity test in July 1945, he tore paper into small scraps and dropped them when the blast wave arrived, then measured how far the pieces blew to estimate the yield of the bomb. This is the quintessential Fermi problem. You don't need precision instruments. You need a genius with scraps of paper and a sense of scale. 5 years later, in the summer of 1950, 4 physicists walked to lunch at Fuller Lodge, Los Alamos National Laboratory. Fermi, Edward Teller, Emil Konopinski, and Herbert York from Berkeley. The conversation started with a cartoon. Alan Dunn had published a drawing in The New Yorker on May 20th that year, showing little green men climbing out of a flying saucer and stealing trash cans from a New York City street. It was a joke about 2 contemporary mysteries: the rash of UFO sightings and the strange disappearance of public garbage cans from the city. The physicists found it funny. They discussed flying saucers for a while, debated whether faster-than-light travel was possible. Teller estimated the probability of seeing evidence for it within 10 years at 1 in a million. Fermi, characteristically, said it was more like 10%. Then the conversation moved to other things, and then, after a gap, after they had been talking about something entirely unrelated, Fermi suddenly blurted out a question. Each of the 3 surviving participants remembered it slightly differently when they were asked about it decades later. Teller recalled it as, "Where is everybody?" York remembered, "Don't you ever wonder where everybody is?" Konopinski heard, "But where is everybody?" What they all agreed on was the strange fact that despite the question coming completely out of the blue, everyone at the table understood instantly that Fermi was talking about extraterrestrial life. Teller recalled that the result of the question was general laughter. Then Fermi did what Fermi always did. He grabbed the back of an envelope and started calculating star formation rates, probability of planets, probability of life, probability of intelligence, timescales for colonization. Within minutes, he had convinced himself that Earth should have been visited many, many times over. The galaxy is roughly 10 billion years old. Even at modest speeds, a civilization could colonize the entire thing in 5 to 50 million years. That is a tiny fraction of the galaxy's age. If anyone, anywhere, at any point in the last 10 billion years had developed the technology and the desire to expand, they would have been here long ago. So where is everybody? Fermi died of stomach cancer on November 28, 1954, at 53. The architect of the nuclear age never lived to see Sputnik, never saw the first radio telescope pointed at the stars, never heard the silence that would haunt every physicist who came after him. But his question, the one he asked between bites of lunch and never published, became arguably the most famous unsolved problem in all of science. And it is a real problem, not a curiosity, not a parlor game. The numbers make it genuinely difficult to explain the silence. Think about it this way. As of early 2026, astronomers have confirmed over 6,000 exoplanets. The Kepler Space Telescope, before it ran out of fuel in 2018, established that planets are not rare. They are everywhere. Essentially, every star has at least one. The current best estimate is roughly 1.6 planets per star on average. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. That gives us, conservatively, hundreds of billions of planets in our galaxy alone. A 2020 study combining Kepler and Gaia data, published in the Astronomical Journal, estimated roughly 300 million potentially habitable planets in the Milky Way. 300 million worlds sitting in the zones around their stars where liquid water could exist on the surface. Now multiply that by the number of galaxies in the observable universe. That number is contested. A 2016 study by Consolis and colleagues estimated at least 2 trillion galaxies. More recent analyses using data from the New Horizons spacecraft's cosmic optical background measurements have suggested a lower number, perhaps several hundred billion. Take the conservative end, several hundred billion galaxies, each with hundreds of billions of stars, each star with roughly 1 or 2 planets. The total number of planets in the observable universe comes out to something in the neighborhood of 10 to the 24th power. That is a 1, followed by 24 zeros. It is more than the number of grains of sand on every beach on Earth. The universe is 13.787 billion years old, give or take 20 million. Earth formed 4.5 billion years ago. Life appeared on Earth almost immediately in geological terms, within the first 500 to 700 million years. This suggests that abiogenesis, the leap from chemistry to biology, may not be the impossibly rare event some have assumed. If life appears quickly wherever conditions allow, then the universe has had billions of years and trillions of chances. In November 1961, a young radio astronomer named Frank Drake organized a small conference at the Green Bank Observatory in West Virginia. He had recently conducted the first modern SETI experiment, Project OSMA, pointing the 85-foot Tattel telescope at 2 nearby stars, Epsilon Eridani and Tau Ceti, and listening for radio signals. He named the project after Princess Ozma of Oz, who lived in a place very far away, difficult to reach, and populated by strange and exotic beings. He found nothing, though an initial false alarm from Epsilon Eridani briefly excited the team. The Green Bank conference was small, 10 people. But what are 10 people? A young Carl Sagan, Philip Morrison, who had co-authored the first scientific paper proposing SETI just 2 years earlier, Barney Oliver from Hewlett-Packard, neuroscientist John Lilly, who was trying to decode dolphin communication, and chemist Melvin Calvin, who received his Nobel Prize in Chemistry during the meeting. The organizer, J. Peter Pearman, had smuggled in champagne for the occasion. The group called themselves the Order of the Dolphin after Lilly's work. A few days before the conference, Drake needed an agenda. He sat down and wrote what became the most famous equation in astrobiology: N equals R star times F sub P times N sub E times F sub L times F sub I times F sub C times L. The number of communicating civilizations in the galaxy equals the rate of star formation, times the fraction of stars with planets, times the number of habitable planets per system, times the fraction that develop life, times the fraction that develop intelligence, times the fraction that develop detectable technology, times the average lifetime of such a civilization. Drake's equation was never meant to produce a definitive answer. It was an organizing framework, a way of breaking an impossible question into component parts. But here is what has happened in the 6 decades since he wrote it. The first few variables have been pinned down. R star, the star formation rate, is well constrained at roughly 1.5 to 3 new stars per year in the Milky Way. F sub P, the fraction of stars with planets, has converged to essentially 1. Kepler proved that planets are ubiquitous. N sub E, the number of habitable planets per system, is estimated at roughly 0.1 to 0.4. These are no longer wild guesses. They are measured values. The remaining variables, the fraction of habitable planets that actually develop life, the fraction of those that develop intelligence, the fraction that develop technology, and the lifetime of technological civilizations, remain deeply uncertain. They could each span many orders of magnitude, but even conservative estimates, plugging in pessimistic numbers for every unknown variable, tend to produce n values that are uncomfortably greater than 1. In 1975, physicist Michael Hart formalized the argument that Fermi had sketched on the back of an envelope. In a paper in the Quarterly Journal of the Royal Astronomical Society, titled An Explanation for the Absence of Extraterrestrials on Earth, Hart pointed out that even at modest expansion speeds, a civilization could colonize the entire galaxy in 5 to 50 million years. The galaxy is roughly 1,000 times older than that timescale. If even one civilization, at any point in the last 10 billion years, had begun expanding, they would have filled the galaxy long ago. Their absence on Earth, Hart argued, is strong evidence that we are alone. But being alone in a universe of 10 to the 24th planets requires an explanation too. Something, somewhere along the chain from dead matter to galaxy-spanning civilization, must be extraordinarily unlikely. In 1996, an economist named Robin Hanson gave this bottleneck a name that stuck: the Great Filter. Hanson, who had been a NASA research programmer before earning his PhD in social science from Caltech, identified 9 evolutionary steps between a habitable star system and an expanding civilization. The Great Filter is whichever of those steps has an astronomically low probability of success. The crucial question is whether the filter is behind us or ahead of us. If the filter is behind us, if the hard part was something like the origin of life or the leap from prokaryotes to eukaryotes, or the development of complex multicellular organisms, then we have already beaten the longest odds. The silence means the early steps are nearly impossible, and we are the lucky ones who made it through. That is the optimistic scenario. If the filter is ahead of us, if there is something that reliably destroys civilizations after they reach a certain level of technological development, then the silence is a warning. We are heading toward whatever killed everyone else. This produces one of the most counterintuitive results in all of science. Finding simple alien life on Mars would be bad news. Not because Martian bacteria are dangerous, because their existence would mean that abiogenesis is easy, that the early steps are not the filter, and therefore the filter must be ahead of us, waiting. Now here is the thing about all of these explanations. They share an assumption. They assume the silence is real. They assume that when we point our telescopes at the sky and see no evidence of civilization, it is because there is no evidence to see. The Planetarium Hypothesis asks a different question. What if the evidence is there, but someone is intercepting it? What if the silence is not absence but censorship? Before Baxter proposed his planetarium, there was a simpler version of the idea. In 1973, a radio astronomer named John Ball, who worked at the Harvard-Smithsonian Center for Astrophysics and MIT's Haystack Observatory, published a 3-page paper in the journal Icarus titled The Zoo Hypothesis. Ball's proposal was elegant. Advanced civilizations, he suggested, deliberately avoid contact with younger species like humanity. They treat Earth the way we treat a wildlife preserve. We are not ignored. We are being watched. But contact is forbidden, perhaps by something like Star Trek's Prime Directive, an ethical commitment to non-interference. Ball himself acknowledged a darker variant, which he called the laboratory hypothesis. The idea that we are not a wilderness preserve, but an experiment. He called this possibility morbid and grotesque. The zoo hypothesis has a certain appeal. It explains the silence without requiring us to be alone. It flatters us, in a way, by suggesting we are interesting enough to watch. But it has a fatal weakness, and this is where Baxter's contribution becomes important. The zoo hypothesis can explain why we do not receive deliberate signals. A galactic civilization could choose not to broadcast in our direction. It can explain why we have not been visited. They could choose to stay away. But it cannot explain why we see no accidental evidence whatsoever. No waste heat from galaxy-spanning infrastructure, no megastructures transiting distant stars, no stray electromagnetic leakage from civilizations that span millions of worlds. The universe should be leaking evidence of advanced life the way a city leaks light. You can see Las Vegas from space, not because Las Vegas is trying to signal you, but because it cannot help being bright. A civilization harnessing the energy of a star, let alone a galaxy, should be visible whether it wants to be or not. Duncan Forgan made this point quantitatively in a 2011 paper in the International Journal of Astrobiology. He showed that maintaining either a zoo or a non-interference pact across galactic scales would be extraordinarily difficult. Speed of light limitations make enforcing universal hegemony over billions of years and hundreds of billions of star systems implausible. Even one defector, one civilization that breaks the pact and broadcasts a signal or builds a visible megastructure would shatter the illusion. And over billions of years, across billions of potential civilizations, the probability of perfect compliance is effectively zero. So passive hiding does not work. The zoo hypothesis fails because it cannot suppress accidental evidence. The universe should not look this empty unless the emptiness is being actively maintained. And that is precisely what the Planetarium Hypothesis proposes. It is not that aliens are choosing to be quiet. It is that someone has built a machine to make them invisible. Think of it this way. A planetarium, the kind you visit on a school field trip, works by projecting an artificial sky onto a dome above your head. You sit in a dark room and you see stars, constellations, the Milky Way. None of it is real. All of it is a projection. But from inside the dome, if the projection is good enough, you cannot tell the difference. Now imagine scaling that dome up, not to the size of a building, to the size of a solar system. Replace the optical projector with something that can generate every kind of signal we know how to detect. Visible light, radio waves, X-rays, gravitational waves, cosmic rays, neutrinos. Every photon that reaches Earth from beyond our solar system, every particle, every ripple in space-time is being manufactured. The real universe, the one behind the dome, could be teeming with civilizations, blazing with the light of 1 trillion Dyson spheres, humming with radio traffic. We would never know. We would see only what the projectors show us, which is silence. Is this physically possible? Baxter's calculation says yes, but only barely, and only for a civilization of almost inconceivable power. On the Kardashev scale, which the Soviet astronomer Nikolai Kardashev proposed in 1964, civilizations are classified by their energy consumption. A Type 1 civilization harnesses all the energy reaching its planet from its star, roughly 10 to the 17th watts for Earth. We are not even there yet. Using Carl Sagan's interpolation formula, humanity currently rates about type 0.73, consuming around 19 terawatts. A type 2 civilization harnesses the entire output of its star, about 3.8 times 10 to the 26th watts. A type 3 civilization harnesses the energy of its entire galaxy, roughly 4 times 10 to the 37 watts. Baxter's planetarium requires a type 3. Nothing less would suffice. And even at type 3, there is a ceiling. The simulation works for a civilization confined to a single planet or a single solar system. But if the contained species expands to span roughly 100 light years, the amount of data that must be faked, the number of signals that must be intercepted and replaced, the coordination required across that volume of space exceeds even galactic-scale resources. The planetarium has an expiration date. It is a cage that works only as long as the captive species stays small. Now, you might be thinking that this sounds a lot like the simulation hypothesis, the idea that we might be living in a computer simulation popularized by the philosopher Nick Bostrom in a 2003 paper, has become so culturally pervasive that it is easy to blur the two together. Movies, podcasts, late-night conversations after too many drinks. Are we in a simulation? Is any of this real? But the planetarium hypothesis and the simulation hypothesis are profoundly different, and the difference matters enormously. It is the difference between being lied to about one thing and being lied to about everything. In Bostrom's simulation, nothing is real. Not the ground under your feet, not the air in your lungs, not the neurons in your brain that are right now processing these words. Everything including you, including your consciousness, is software running on alien hardware. The entire universe, from the cosmic microwave background to the inside of your coffee cup, is a computation. In Baxter's Planetarium, you are real. The Earth is real. Your body, your brain, the coffee cup, the air, the ground, all of it is genuine physical matter in a genuine physical universe. The only thing that is fake is what your telescopes see when you point them at the sky. You are a real person being shown a false view. You are not a simulation of a person. You are a person in a planetarium. This distinction has enormous consequences for energy and computation. In 2025, Franco Vazza, an astrophysicist, published a paper in Frontiers in Physics titled Astrophysical Constraints on the Simulation Hypothesis for this Universe. He calculated the information required to simulate the entire observable universe at quantum resolution. The number is 3.5 times 10 to the 124th power bits. The energy to encode that much information would be 8.9 times 10 to the 108th power ergs. To put that in perspective, the total energy contained in the entire observable universe is about 10 to the 78th power ergs. The energy required to simulate the universe exceeds the energy the universe actually contains by a factor of roughly 10 to the 30th power. It is not just difficult. It is not just impractical. It is physically impossible by a margin of 1,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,0 simulate just Earth at quantum resolution. That requires 9.8 times 10 to the 74th power bits of information. The energy just to initialize that simulation, to set up the starting conditions, would be equivalent to the rest mass energy of a globular cluster, which is a ball of hundreds of thousands of stars. And even then, advancing the simulation by a single second of Earth time would require more computational operations per bit per second than any conceivable computer could perform. The operations per bit per second requirement comes out to roughly 10 to the 31st power. The best theoretical computing limits, based on Bremerman's limit and the Margolis-Levitin theorem, max out at about 10 to the 15th or 10 to the 17th. That is a gap of 14 orders of magnitude. A full quantum simulation of Earth cannot run in real time. A single second of simulated time would take millions of real years to compute. So the full simulation hypothesis, in its strongest form, is dead on arrival. The universe contains too much information to be copied. It is not a question of building a bigger computer. The computer would need to be bigger than the universe it is simulating, which is a logical impossibility. But the planetarium does not need to simulate everything. It only needs to simulate what reaches our instruments. It needs to fake the cosmic microwave background radiation, which is a two-dimensional surface of roughly 10 to the 51 bits. It needs to generate convincing starlight, radio emissions, X-ray sources, gravitational wave signals, cosmic ray spectra, and neutrino fluxes consistent with an empty universe. That is still an enormous amount of information, perhaps 10 to the 51 to 10 to the 75th bits, depending on the fidelity required. But it is anywhere from 50 to 70 orders of magnitude, less than a full simulation. It is the difference between faking a movie set and creating an actual world. One is engineering. The other is magic, a Type 3 civilization pouring the energy of 400 billion stars into the task, operating at the thermodynamic limits of computation, could conceivably generate and maintain a fake sky of this quality. Not easily, not cheaply, not indefinitely, but possibly. And that possibly is what separates the Planetarium Hypothesis from pure science fiction. The question that should be forming in your mind right now is whether there is any way to tell if the planetarium is good enough, if the fake sky is perfectly consistent with the real universe we think we live in. Then by definition, we cannot detect the deception. The perfect crime leaves no evidence. But here is where things get interesting. There are reasons to think a perfect planetarium might be very, very hard to build. And some of those reasons come from the deepest unsolved problems in physics. Start with the cosmic microwave background. The CMB is the afterglow of the Big Bang, a bath of microwave radiation that fills the entire sky at a temperature of about 2.725 Kelvin. It is the most precisely measured radiation in the history of science. The Planck satellite, which observed it from 2009 to 2013, measured its temperature to a precision of millionths of a degree across the full sky. If the planetarium is generating a fake CMB, it needs to be consistent to this precision, and it needs to be consistent not just in temperature, but in the detailed statistical properties of the tiny fluctuations, the acoustic peaks, the polarization patterns, the spectral distortions. The real CMB encodes the physics of the entire universe at an age of 380,000 years. Faking it convincingly means either understanding the real universe well enough to reproduce all of its properties, which requires knowing the actual physics behind the dome, or simply copying the real CMB and hoping nobody notices the seams. And this is where the anomalies become fascinating, because there are seams in the CMB, real ones, confirmed by multiple satellite missions, and nobody knows what they mean. In 2004, a team using wavelet analysis of WMAP data discovered the CMB cold spot, an anomalously cold region about 5 degrees across in the constellation Eridanus, surrounded by an unusually hot ring. The Eridanus supervoid, potentially one of the largest structures ever identified, may partially explain it through the integrated Sachs-Wolf effect, but the correlation is marginal. In 2005, Kate Land and João Magejo at Imperial College London published a paper in Physical Review Letters with one of the best titles in the history of physics. They found that the lowest frequency oscillations in the CMB, the quadrupole and octupole patterns, are anomalously aligned with each other and, astonishingly, with the plane of the solar system. They called this alignment the axis of evil. The alignment extends up to the 5th multipole and rejects statistical isotropy, meaning randomness, at greater than 99.9% confidence. This was confirmed by the Planck satellite. It is not a measurement error. It is a real feature of the data. Lawrence Krauss, the theoretical physicist, put it bluntly. The new results are either telling us that all of science is wrong and we're the center of the universe, or maybe the data is simply incorrect, or maybe there's something wrong with our theories on the larger scales. Add to this the hemispherical power asymmetry, first reported by Ericsson and colleagues in 2004 and confirmed by Planck at 98 to 99% confidence. One half of the sky has slightly more CMB power than the other. a Monte Carlo analysis found that the joint likelihood of these anomalies combined is incompatible with our standard model of cosmology at greater than 99.95% confidence. Now, to be clear, no mainstream physicist proposes that these anomalies are evidence of artificial manipulation. The most likely explanations involve foreground contamination, statistical flukes in a universe that only gives us one sky to measure, or genuinely new physics at the larger scales. But for the purposes of this video, what matters is that the CMB is not a perfectly smooth, perfectly understood backdrop. It has features that we cannot explain. If you were a planetarium engineer, these would be exactly the kind of artifacts you might worry about. Tiny inconsistencies, alignment artifacts that shouldn't be there, features that point suspiciously at the observer. The Planck data also reveals something else that is relevant. The fluctuations in the CMB are Gaussian to an extraordinary degree. This means they follow a random bell curve distribution, which is exactly what you would expect from quantum fluctuations in the early universe. But it is also, in a different light, exactly what you would expect from a well-designed noise generator. Random noise is what you produce when you want to create a convincing backdrop without hiding any information in it. This is not an argument that the CMB is fake. It is an observation that a perfectly random signal is, by definition, indistinguishable from a perfectly designed one. Let me take a step sideways here, because there is a misconception worth addressing. You will sometimes hear people say that the simulation hypothesis, and by extension the planetarium hypothesis, is unfalsifiable, that it is philosophy, not physics, that it is the modern equivalent of asking how many angels can dance on the head of a pin. This is wrong. In 2012, 3 physicists, Silas Bean, Zohre Davoudi, and Martin Savage, published a paper on the R-Krakov titled Constraints on the Universe as a Numerical Simulation. Their idea was straightforward and clever. If the universe was simulated on a cubic space-time lattice, like the lattices used in the quantum chromodynamics calculations that physicists already run on supercomputers, then the lattice would impose a structure on space-time, and that structure would have observable consequences. Specifically, the highest energy cosmic rays would be constrained by the lattice spacing. There would be a maximum energy cutoff, and the arrival directions of those cosmic rays would not be perfectly isotropic. They would show a slight preference for traveling along the lattice axis, the way a ball rolling on a tile floor moves more easily along the grout lines. The existing data on ultra-high-energy cosmic rays, particularly the GZK cutoff, already constrains the lattice spacing to something finer than 1/10 to the 11th giga-electronvolt. But the key point is not that they found evidence of a lattice. They did not. The key point is that they showed exactly what evidence to look for. The hypothesis makes predictions. Those predictions can, in principle, be tested. That is what it means for something to be falsifiable. Zohre Davoudi, who is now an associate professor at the University of Maryland and a recipient of the Kenneth G. Wilson Award and a Sloan Fellowship, has since moved her research toward building the kind of quantum simulations that might one day test these ideas more directly. She works on simulating quantum field theories using trapped ion platforms and quantum computers. In 2016, she sat on a panel at the Isaac Asimov Memorial Debate alongside David Chalmers, Lisa Randall, Max Tegmark, and James Gates, hosted by Neil deGrasse Tyson, discussing whether the universe might be simulated. The debate was notable for how seriously the physicists took the question. Melvin Vopson, a physicist at the University of Portsmouth, has proposed an even more direct test in a 2022 paper in AIP Advances. Vopson suggested that if information has physical mass, as he argues in his mass-energy information equivalence principle, then the annihilation of an electron and a positron should produce not just the expected gamma-ray photons, but also additional low-energy infrared photons at a wavelength of about 50 micrometers. These extra photons would carry away the information content of the annihilated particles, roughly 1.5 bits per elementary particle. If detected, they would demonstrate that information is a physical quantity with measurable consequences. This experiment has not yet been conducted, and Vopson's broader theoretical framework, which he has published primarily in AIP Advances rather than the top-tier journals, has drawn skepticism. Sabine Hossenfelder has criticized the work, and the physics community has not embraced it. But the fact that someone can propose a specific, concrete laboratory experiment whose result would bear on the question of whether information is physically real, and therefore on whether the universe could be an information construct, is significant. It means we are not in the realm of pure philosophy anymore. We are at the boundary where philosophy is beginning to acquire experimental handles. There is a deeper reason why the Planetarium Hypothesis is not immediately absurd, and it has to do with what physicists have been discovering about the nature of reality itself over the last 30 years. This is where the story takes a turn that even Baxter might not have anticipated when he wrote his paper. In 1993, the Dutch theoretical physicist Gerard 't Hooft proposed something radical. He suggested that the physics of any volume of space can be completely described by information encoded on the boundary of that volume. Not approximately described, completely described. The number of degrees of freedom is proportional to the area of the boundary, measured in Planck units, not to the volume of the space enclosed. This means that a three-dimensional region of space contains no more information than can be painted on its two-dimensional surface. Leonard Susskind elaborated the idea in a landmark 1995 paper in the Journal of Mathematical Physics titled "The World as a Hologram." He wrote, and I want to read this carefully because it sounds like science fiction, but it is not. The three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant two-dimensional surface. This is the holographic principle, and it is not a fringe idea. It is one of the most important and well-supported theoretical developments in physics since general relativity. In 1999, Juan Maldacena provided the most concrete realization through what is called the ADS/CFT correspondence, showing that a gravity theory in a particular kind of curved spacetime is exactly mathematically equivalent to a quantum field theory living on the boundary of that spacetime. Maldacena's paper has been cited over 25,000 times. It is one of the most influential physics papers ever written. What the holographic principle tells us, if it is correct, is that three-dimensional space might be, in some deep sense, a projection. The real physics lives on a two-dimensional surface, and the three-dimensional world we experience is an emergent image, like a hologram reconstructed from a flat plate. This does not mean the three-dimensional world is fake. It means that information, not matter, is the fundamental substrate. The universe is not made of stuff. It is made of data. And the three-dimensional stuff we interact with is one way of reading that data. John Archibald Wheeler saw this coming 30 years before anyone else. Wheeler was born on July 9th, 1911, to librarian parents. As a small child, while being given a bath, he asked his mother a question that he would spend his entire career trying to answer. What happens when you get to the end of things? He entered Johns Hopkins University at 16. He had his PhD by 21. He spent a postdoctoral year with Niels Bohr in Copenhagen. On his fellowship application, he wrote that he wanted to study with Bohr because he sees further ahead than any man alive. Wheeler's impact on physics is almost impossible to overstate. He popularized the term black hole starting in 1967. Stephen Hawking called him the hero of the black hole story. He coined wormhole in 1957. He invented the concepts of quantum foam and space-time foam. His first doctoral student was Richard Feynman, who won the Nobel Prize in 1965. He also supervised Kip Thorne, who won it in 2017, Hugh Everett III, who proposed the many worlds interpretation, and Jacob Bekenstein, who discovered the fundamental limit on information in a region of space. Over the course of his career at Princeton, Wheeler supervised 46 doctoral students, more than any other physics professor. But there is a personal dimension to Wheeler's story that connects to the physics in ways that are almost too poignant to be real. Wheeler's younger brother Joe was a PhD historian who served as an army officer in the Second World War. While stationed in Italy, Joe sent John a 2-word postcard. Hurry up. Joe was killed in combat on October 25th, 1944, in northern Italy. Wheeler was devastated. He later wrote that he could not stop thinking, and had never stopped thinking, that the war could have been over in October 1944 if the bomb had been ready. He calculated that roughly 500,000 to 1 million people were dying per month in the final stages of the war. His daughter Letitia recalled that as Wheeler got older, he wept often over his brother, and a colleague once noted that Wheeler had all but cried when calculations showed that Einstein's theory ruled out wormhole travel. The colleague believed Wheeler had been hoping to use a wormhole to see the brother he had lost. In the spring of 1989, at a conference at the Santa Fe Institute, Wheeler, then 78 years old, gave a talk that would become the capstone of his career. He called it from bit. His declaration: every it, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely from the apparatus elicited answers to yes or no questions, binary choices, bits. Reality, Wheeler argued, is not made of matter. It is not made of energy. It is made of information, and the universe is participatory. Observers do not passively watch reality unfold. They participate in creating it by asking questions, by making measurements, by forcing the universe to give yes or no answers. Information creates physics. Physics creates observers. Observers create information. The loop closes on itself. Wheeler died on April 13th, 2008, at 96. He was the last living person to have worked with both Einstein and Bohr, and his final intellectual contribution, the idea that reality is made of information, turns out to be the single concept that makes the Planetarium Hypothesis thinkable. Because if the universe is fundamentally informational, if three-dimensional space is a holographic projection, if the physics of gravity can be derived from thermodynamic properties of information, then faking a piece of that information is not faking matter. It is altering data. And altering data, while still enormously difficult, is a categorically different problem than creating physical reality from scratch. Eric Verlinde extended Wheeler's trajectory in a striking way in a 2010 paper published in the Journal of High Energy Physics. Verlinde argued that gravity is not a fundamental force at all. It is an entropic force arising from statistical changes in the information associated with matter's position. He derived Newton's law of gravitation, the inverse square law that holds apples to the ground and planets in their orbits, from the holographic principle and the laws of thermodynamics. Gravity, in Verlinde's picture, is what happens when the information content of a region changes as matter moves. It is an emergent phenomenon, like temperature or pressure. A 2016 study from Leiden Observatory found gravitational lensing data from over 33,000 galaxies consistent with Verlinde's predictions, though a 2017 Princeton study found inconsistencies with the rotation curves of dwarf galaxies. If Verlinde is right and gravity is information, then the force holding you in your chair right now is a consequence of data processing. The planet beneath you, the star that warms you, the galaxy that contains you, all are emergent structures arising from underlying information dynamics. Wheeler's "it from bit" is not a metaphor. It is a physical claim about the nature of reality. And this brings us back to the planetarium. If the universe is information, and the sky is part of that information, then manipulating the sky is an information processing problem. A very large one, an almost inconceivably large one, but not a fundamentally different kind of problem from the information processing the universe is already doing. A Type 3 civilization commanding the computational resources of a galaxy would be in the business of manipulating information at a scale we can barely imagine. Building a planetarium, faking the sky, would be a vanity project, an expensive one, but not an impossible one. The question is whether they would, and the question after that is whether we could tell. And that second question depends on how deep the physics goes, because there are features of our universe, features we have measured with exquisite precision, that look exactly like the kind of thing you would expect to find if the universe were engineered. Consider the cosmological constant. This is the single most embarrassing number in all of physics. Quantum field theory, which is the most precise theory humans have ever constructed, predicts that empty space should be seething with energy. The predicted vacuum energy density is enormous, calculated at the Planck scale of 10 to the 18th giga-electronvolts to the 4th power. The observed value, the actual amount of vacuum energy driving the accelerating expansion of the universe, is roughly 120 orders of magnitude smaller. That is not a rounding error. That is a discrepancy of a factor of 10 to the 120th power. Steven Weinberg, the Nobel laureate, put it this way: "The existence of life of any kind seems to require a cancellation between different contributions to the vacuum energy, accurate to about 120 decimal places." Leonard Susskind was even more direct. To make the first 119 decimal places of the vacuum energy zero is most certainly no accident. This is the largest disagreement between theory and experiment in the history of science. Nothing else comes close, and the fine-tuning does not stop there. Martin Rees, who has been Britain's Astronomer Royal since 1995, identified 6 fundamental numbers that shape the universe. N, the ratio of electrostatic to gravitational force between 2 protons, is approximately 10 to the 36th power. If it was significantly smaller, the universe would be too cold and small for complexity. Epsilon, the nuclear binding efficiency, is roughly 0.007. If it were 0.006, deuterium would be unstable and stellar nucleosynthesis would fail. If it were 0.008, hydrogen would be consumed too quickly in the Big Bang, and there would be no fuel for stars. Omega, the ratio of the actual density of the universe to the critical density, is close to 0.3. Lambda, the cosmological constant, is close to 0.7. Q, the amplitude of density fluctuations in the early universe, is about 10 to the -5th power. If Q was smaller, matter would never have clumped into galaxies. If larger, the universe would be filled with massive black holes instead of stars. And D, the number of spatial dimensions, is 3. 2 dimensions cannot support the complex structures needed for life. 4 spatial dimensions make stable planetary orbits impossible. Rees's conclusion was blunt. If any one of them were untuned, there could be no stars and no life. He personally favors multiverse explanations, the idea that all possible values of these constants are realized in different regions of a vast multiverse, and we simply find ourselves in one of the rare patches where the numbers permit observers, but he acknowledges the fine-tuning as genuinely remarkable, regardless of its explanation. Now, I want to be careful here. Fine-tuning does not prove design. It does not prove simulation. It does not prove a planetarium. There are multiple legitimate explanations. The anthropic principle says we observe fine-tuned constants because only fine-tuned constants permit observers. It is a selection effect, not evidence of engineering. The multiverse hypothesis says every possible set of constants exists somewhere, and we are necessarily in a hospitable region, and there may be deeper physical theories not yet discovered that make these values natural rather than improbable. But what fine-tuning does is this. It establishes that the universe we observe has properties that are exquisitely, almost absurdly, suited for observers. And if you are asking whether someone could have set those properties deliberately, fine-tuning makes the question harder to dismiss. A planetarium does not need to explain fine-tuning, since in Baxter's version, the physical universe is real and the constants are whatever they are. But the broader landscape of ideas that the planetarium sits within, the landscape that includes simulation and design and engineered realities, draws real nourishment from the fine-tuning problem. The universe looks at the deepest level physicists can probe, as though something went to extraordinary trouble to make it habitable. And there is another piece of physics that connects to all of this, one that most people outside of theoretical physics have never heard of. In 1981, Jacob Bekenstein, one of Wheeler's doctoral students at Princeton, derived a limit on how much information a region of space can contain. The Bekenstein bound states that the maximum entropy, which is to say the maximum information content of a region, is proportional to the area of its boundary and the total energy inside, divided by fundamental constants. Black holes saturate this bound. They are the densest information storage devices in the universe. A black hole contains the maximum possible information for its size, and all of that information is encoded on its two-dimensional surface, its event horizon, not in its volume, on its surface. This was one of the first concrete pieces of evidence for the holographic principle. It says the universe has a finite information capacity. It cannot store infinite data. And if the information is finite, it is, in principle, computable. Not easily, not quickly, but in principle. In 1995, Ted Jacobson pushed this further. He showed that if you start from the Bekenstein bound and the laws of thermodynamics, you can derive Einstein's field equations of general relativity, the equations that describe how matter curves space-time, how gravity works, how the universe expands. They emerge from information and thermodynamics. This is one of the most underappreciated results in modern physics. It suggests that gravity, the force that shapes the large-scale structure of the entire universe, is not fundamental. It is a consequence of information dynamics. And if gravity is information, then the universe is, in a very precise sense, a computational process. Seth Lloyd, a quantum computing pioneer at MIT, quantified this in a 2002 paper in Physical Review Letters titled Computational Capacity of the Universe. Lloyd calculated that the universe, since the Big Bang, has performed no more than 10 to the 120th operations. It can store roughly 10 to the 90th bits of information from conventional entropy considerations, or up to 10 to the 120th bits if you include the gravitational degrees of freedom encoded in black holes. These are staggering numbers, but they are finite. The universe has done a lot of computing, but it has not done infinite computing. It has processed a lot of information, but not unlimited information. And this finitude is, again, a necessary condition for the simulation or planetarium scenarios to be even conceivable. You cannot simulate something that contains infinite information, but you can, in principle, simulate something whose information content has an upper bound. The picture that emerges from all of this, from the holographic principle, from Wheeler's it from bit, from Verlaine's entropic gravity, from Jacobson's derivation of general relativity from thermodynamics, from Lloyd's computational capacity bounds, is a picture in which reality is fundamentally informational. The three-dimensional world is a readout of underlying data. Gravity is an emergent consequence of information dynamics. Space itself may be woven from quantum entanglement, as recent work by Maldacena and others on the ER equals EPR conjecture suggests. In this picture, the distinction between real and simulated starts to blur, because reality itself is already a kind of computation. This does not prove the Planetarium Hypothesis. Nothing proves the Planetarium Hypothesis, but it removes the most obvious objection, which is that faking reality would require building physical objects out of physical matter. If reality is information, then faking a piece of reality means faking a piece of information. And the information can be manipulated, intercepted, replaced. That is not physics fiction. That is, at the deepest level we currently understand, physics fact. But there is a problem with all of this that we need to confront directly. Even if the physics allows for a planetarium, even if the energy budget works for a Type 3 civilization, we have to ask, could we catch them in the act? Is there any observation, any experiment, any anomaly in the data that would let us detect the dome? The honest answer is that we do not know, but we are beginning to have ideas. And some of those ideas come from a surprising direction. The Planck length is approximately 1.616 times 10 to the negative 35th meters. This is unimaginably small. It is roughly 10 to the negative 20th times the diameter of a proton. It is the scale at which both quantum mechanics and general relativity become simultaneously important, the scale at which our current theories of physics break down completely. There is a popular notion that the Planck length represents a kind of pixel, a minimum resolution of space-time, like the pixels on a screen. If you zoom in far enough, you eventually see the grid. This notion has been enthusiastically embraced by simulation hypothesis proponents, who argue that the Planck scale is evidence that reality has a minimum resolution, just like a computer simulation. This is a misconception, and it is worth correcting carefully, because the truth is actually more interesting than the myth. The Planck scale is not a pixel, it is a horizon. If you try to localize something at the Planck scale, the energy required to do so is so enormous that a black hole forms that is larger than the region you are trying to probe. You lose the ability to localize. It is not that space-time is made of tiny blocks. It is that the very concept of spatial resolution ceases to be meaningful below a certain scale. One physicist described it as more like trying to squeeze water in your hand. It squishes out from the sides. The Planck length is not a minimum distance. It is a minimum meaningful distance. There is a subtle but important difference. That said, some approaches to quantum gravity do predict genuine discreteness. Loop quantum gravity, developed by Carlo Rovelli and Lee Smolin starting in the late 1980s, predicts the quantum operators for area and volume have discrete eigenvalues. Space in this picture really does come in minimum chunks. The smallest possible area is roughly the Planck area, about 2.6 times 10 to the negative 66 square centimeters. The smallest possible volume is roughly the Planck volume. These are not pixels in the simulation sense, because they arise from the quantization of geometry itself, not from a computational grid. But the observable consequences could, in principle, be similar. Can we detect this discreteness? Possibly. In 2015, the Fermi Large Area Telescope observed a gamma-ray burst called GRB 090510 from a distance of about 7 billion light-years. 3 photons with energies differing by about 30 giga-electron-volts arrived within approximately 1 millisecond of each other after traveling for 7 billion years. This is extraordinary precision. It constrains the smoothness of space-time to better than 1/500th of the Planck length for certain models of dispersion. Space-time, as far as we can measure, is smooth. If there is a lattice, it is finer than anything we can currently detect. But in 2022 and 2023, the LHASO Observatory in China detected an 18 TeV photon from the extraordinarily bright gamma-ray burst GRB 221009A, and the data shows a possible hint of subliminal Lorentz invariance violation, meaning the photon may have traveled very slightly slower than it should have. This is tentative. It is disputed. But if confirmed, it would be exactly the kind of signal that a lattice structure in space-time would produce. The point is not that we have found the grid. We have not. The point is that we know what to look for. We are building instruments capable of looking, and the answer is no longer guaranteed to be boring. And then there are the searches for the civilizations themselves, because even if the planetarium is hiding evidence of alien life, maybe the hiding is imperfect. Maybe something is leaking through. Maybe we are close to seeing something that should not be there. In June 2024, a team running what they called Project Hephaestus published results in the monthly notices of the Royal Astronomical Society. They had searched for Dyson spheres, hypothetical megastructures built around stars to capture their entire energy output. What they found were 7 M-dwarf stars within roughly 1,000 light-years of Earth, showing unexplained mid-infrared excess. The infrared signature is consistent with what a partial Dyson sphere would produce, warmth radiating from a structure absorbing and reprocessing starlight. A complementary study found about 53 additional candidates among brighter stars. Before you get too excited, subsequent analysis revealed that at least 3 of the 7 original candidates are likely contaminated by background galaxies, specifically hot dust-obscured galaxies, whose infrared emission mimics a Dyson sphere signature. The remaining candidates are genuinely unexplained, but unexplained is a long way from confirmed alien megastructure. Natural explanations, like extreme debris disks, remain on the table. But consider what it would mean for the Planetarium Hypothesis if any of those candidates turned out to be real. It would mean the dome is leaking. The projector has a flaw. The fake sky has, somewhere, a star that does not behave the way empty universe stars should behave, because behind the projection, someone built something around it, and the planetarium could not fully mask the infrared signature. This is speculative, obviously, but it illustrates how the Planetarium Hypothesis converts every unexplained astronomical observation into a potential clue. The Breakthrough Listen project, which moved its headquarters to the University of Oxford in 2024 and developed an AI system with NVIDIA that processes data 600 times faster than previous methods, has been listening harder than anyone in history. They observed the third known interstellar object, 3I/Atlas, discovered in July 2025 across multiple facilities. No techno-signatures were detected. SETI at Home's comprehensive final analysis, published by Corpella and colleagues in 2025, found no repeatable detections across the entire Arecibo dataset. China's FAST telescope, the largest single-dish radio telescope in the world, launched the Far Neighbor project in 2023 and conducted a deep search of the TRAPPIST-1 system at frequencies between 1.05 and 1.45 gigahertz. Nothing. The silence continues. 75 years after Fermi's question, with instruments billions of times more sensitive than Frank Drake's 85-foot telescope at Green Bank, the universe remains stubbornly, profoundly quiet. Drake spent 62 years of his life listening for a reply, He co-designed the Pioneer plaque, wrote the Arecibo message, and helped engineer the Voyager Golden Record. He served as president of the SETI Institute Board for 19 years. Seth Shostak, a colleague, remembered him as one of the last nice guys around, never moody, never angry. Drake died on September 2nd, 2022, at 92, at his home in Aptos, California. His daughter Nadia wrote, "Dad leaves a titanic absence. He spent more than 6 decades listening for a signal that never came. He never heard a reply, and neither has anyone else. Either nobody is out there, which the numbers make extremely difficult to believe, or they are out there, but something is preventing us from hearing them. And the most radical version of that something is a machine built to make the sky look empty. The question is whether we are stuck in a philosophical loop, endlessly speculating about something we can never test, or whether the physics is giving us, slowly, reluctantly, tools that might one day let us poke a hole in the dome. Because in 2025, something happened that shifted the terms of this debate. A philosopher, a physicist, and a mathematician all published papers within months of each other that attempted, for the first time, to put the simulation and a planetarium questions on rigorous formal footing. And what they found does not settle anything, but it opens doors that previous generations of thinkers could not even locate, let alone knock on. Before we get to those papers, though, we need to reckon with the man who started the modern version of this conversation. A Swedish philosopher who built one of the most influential research institutes in the world, watched it collapse around him and left behind a trilemma that refuses to die. Nick Bostrom was born Nicholas Bostrom on March 10, 1973, in Sweden. His academic background is almost absurdly broad, spanning theoretical physics, computational neuroscience, mathematical logic, artificial intelligence, and philosophy. In 2003, he published a paper in the Philosophical Quarterly that would make him one of the most cited philosophers alive. The paper is called "Are You Living in a Computer Simulation?" and his argument is deceptively simple. Bostrom starts with a single assumption: substrate independence. The idea that consciousness does not require biological neurons specifically, that it can, in principle, be reproduced on any sufficiently complex computational structure. If you accept substrate independence, then a sufficiently powerful computer could simulate conscious minds. Those simulated minds would experience a world, have thoughts, feel real, and they would have no way of knowing they were simulated. From this, Bostrom derives a trilemma. At least one of 3 propositions must be true. First, nearly all civilizations go extinct before reaching the technological capability to run large-scale simulations of conscious minds. Second, virtually no civilizations that reach that capability choose to run such simulations. Or third, we are almost certainly living in a simulation right now. The logic is probabilistic. If civilizations routinely survive to the post-human stage and routinely run ancestor simulations, then the number of simulated minds in the universe would overwhelmingly exceed the number of biological minds. You would be like a single grain of real sand in a desert of artificial grains. Pick a grain at random, and the odds are overwhelming that it is artificial. If you have no special reason to believe you are the rare biological original, the bland principle of indifference says you should assign near certain probability to being simulated. The only way to avoid this conclusion is to deny one of the first two propositions. Either civilizations almost always die before they can run simulations, or civilizations that survive almost never choose to run them. Bostrom does not tell you which proposition is true. He tells you that one of the three must be. Now, Bostrom's trilemma and Baxter's planetarium are addressing related but fundamentally different questions. I said this earlier, but it is worth returning to with more precision, because the distinction matters and most people blur it. In Bostrom's scenario, the simulation is total. Everything is computed. The atoms in your body, the neurons in your brain, the photons hitting your retina, the quarks inside the protons inside the atoms, inside the coffee in your cup. All of it. There is no base reality to stand on. You are software experiencing a software world. In Baxter's scenario, you are standing on solid ground. Literally, your atoms are real atoms. Your neurons are real neurons. The only thing being simulated is the data that arrives from outside your solar system. You are a real person watching a fake movie projected onto the sky. The computational difference between these two scenarios is not a matter of degree. It is a matter of category. Vaza's 2025 numbers make this viscerally clear. Simulating everything requires 10 to the 124th power bits of information and 10 to the 108th power ergs of energy, which is 10 to the 30th times more energy than the entire observable universe contains. That is not a number you can engineer around. That is a number that says no. Simulating only the sky requires something like 10 to the 51st to 10 to the 75th bits. Still monstrous, still beyond anything humanity can imagine building, but within the theoretical envelope of a Type 3 civilization. The chasm between these two numbers, 50 to 70 orders of magnitude, is the chasm between impossible and merely implausible. In November 2005, Bostrom founded the Future of Humanity Institute at the University of Oxford. FHI grew from 3 researchers to roughly 50 at its peak. It became the intellectual hub for a constellation of ideas that would reshape how serious people thought about the future: existential risk, effective altruism, long-termism, AI alignment, the vulnerable world hypothesis. Bostrom's 2014 book, Superintelligence, became a New York Times bestseller and was endorsed by Elon Musk and Bill Gates. Then things fell apart. In January 2023, a 1996 email surfaced in which Bostrom had used shockingly racist language. His public apology was widely criticized for its tone, for repeating the original slur, and for an irrelevant digression about eugenics that managed to make things worse. Oxford launched an investigation. The broader effective altruism ecosystem, already reeling from the Sam Bankman-Fried fraud, which ended in a 25-year prison sentence, distanced itself. And the Faculty of Philosophy at Oxford, which had been restricting FHY's ability to raise funds and hire since 2020, tightened its grip. An internal joke measurement circulated among the staff. One Oxford was defined as the amount of work needed to read and write 308 emails. On April 16th, 2024, the Future of Humanity Institute closed its doors. Anders Sandberg, one of its longest-serving researchers, wrote a final report attributing the collapse to gradual suffocation by faculty bureaucracy. Bostrom resigned from Oxford and founded a new non-profit, the Macro Strategy Research Initiative. The irony is considerable. A man who spent his career thinking about existential threats to civilization watched his own institution destroyed not by any of the grand risks he studied, but by the accumulated friction of academic politics. The trilemma survived, though. Ideas are harder to kill than institutes. But while Bostrom was grappling with the question of total simulation, a Canadian science fiction author had been thinking about the problem from a completely different angle, and his insight offers what might be the most elegant alternative to the planetarium: the idea that advanced civilizations do not need to hide, because sufficiently advanced technology hides itself. Carl Schroeder, in his 2002 novel Permanence and a widely cited 2011 blog post titled The Deepening Paradox, rephrased Arthur C. Clarke's famous third law. Clarke said that any sufficiently advanced technology is indistinguishable from magic. Schroeder said, any sufficiently advanced technology is indistinguishable from nature. The reasoning is thermodynamic. SETI searches for waste heat, waste electromagnetic radiation, waste light. A Dyson sphere is detectable because it is hot. A radio-transmitting civilization is detectable because its signals leak into space. We look for extraterrestrial intelligence by looking for inefficiency. But a truly advanced civilization, one that has had millions or billions of years to optimize its technology, would approach perfect thermodynamic efficiency. It would produce no detectable waste. Its technology would acquire, as Schroeder put it, natural technological camouflage, not because it is hiding, because efficient systems, by definition, do not leak. This is different from the planetarium in a crucial way. The planetarium requires intent. Someone has to decide to build the dome, to run the projectors, to maintain the illusion. Schroeder's artificial nature requires nothing but the passage of time and the arrow of optimization. A civilization that has been refining its technology for 1 billion years does not look like a civilization anymore. It looks like physics. It looks like nature. We could be staring directly at it and see nothing but stars. The dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin in his 2008 novel The Dark Forest, takes a different path to the same silence. In Liu's vision, the universe is a dark forest filled with armed hunters. Every civilization is a hunter moving silently through the trees. You do not know the intentions of the other hunters. You do not know their capabilities. You know only that resources are finite and survival is uncertain. The rational strategy is to shoot first. Any civilization that reveals its presence, that broadcasts a radio signal or builds a visible megastructure, is painting a target on itself. The silence, in this view, is not the absence of life. It is the sound of every civilization in the galaxy holding its breath. The dark forest does not need a planetarium. It needs only game theory and fear. But it suffers from the same scalability problem as the zoo hypothesis. Over billions of years, across billions of potential civilizations, the probability that every single one independently arrives at the same strategy, and that not one defector ever breaks the silence, strains credulity. The planetarium bypasses this problem by removing the need for universal compliance. You do not need every civilization to agree to be quiet. You need one sufficiently powerful civilization to build a dome. There is one more person whose story belongs in this narrative, and hers is the most unlikely of all. Jill Tarter was born on January 16th, 1944. She lost her father at 12, which taught her, she said later, to seize the day. In high school, she wanted to take woodshop, but was forced into home economics. A scholarship at Cornell was denied because it was reserved for male descendants of Ezra Cornell. She enrolled anyway, as the only woman among 300 engineering students. Nobody made it easy for her. Her career changed when a colleague named Stuart Bowyer handed her a document. It was the Cyclops Report, a 1971 NASA study of the feasibility of searching for extraterrestrial intelligence. 250 pages. Tata read it in a single sitting. She later recalled, "I couldn't imagine anything more fulfilling than using new telescopes to try to answer questions we had been asking for millennia." She spent the next 4 decades doing exactly that. She became the director of the Center for SETI Research at the SETI Institute. She was instrumental in Project Phoenix and later in Breakthrough Listen. Carl Sagan based the character Ellie Arroway in Contact on her. Jodie Foster, who played Arroway in the film, inscribed a photograph to Tata. "Thank you for all of your inspiration." On the night in September 1993, when Congress voted to kill NASA's SETI program, Tata was at the Von Braun lecture series. A staffer whispered the news. She calls that evening a Rocky Mountain high because John Denver performed, and a Death Valley low. The program she had spent years building, the first federally funded search for extraterrestrial intelligence, was dead. She went on to raise millions in private funding to keep the search alive. A woman who had been denied a scholarship because of her sex, who had been the only woman in a room of 300, who had been told explicitly and implicitly that she did not belong, became the single most persistent advocate for the possibility that we are not alone. She has spent more than 50 years looking for a signal. She has not found one. She has not stopped looking. And here is the cruel twist. If the Planetarium Hypothesis is correct, then Tata and Drake before her, and every SETI researcher who has ever pointed a radio dish at the sky and listened, has been listening to static from a machine. Their entire careers, their sacrifices, their stubbornness, their beautiful, relentless optimism has been directed at a projection. The signal they have been searching for could be right behind the dome, blaring, and they would never hear it. Let me bring us to the present, because the story does not end with unanswered questions. It ends with new tools and new papers and new reasons to think the questions might eventually become answerable. The James Webb Space Telescope has been transforming our understanding of exoplanet atmospheres since it began science operations in 2022. But it has not found what everyone is hoping for. No confirmed biosignatures, no definitive evidence of life beyond Earth. In July 2024, a study published in the Astrophysical Journal Letters identified LHS 1140b, a super Earth 48 light-years away, as a particularly promising candidate. The data suggests water may comprise 10 to 20% of the planet's mass, with the possibility of liquid surface oceans. K218b became the loudest exoplanet flashpoint of 2025 when a Cambridge team announced a possible detection of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by living organisms. But the signal is contested. Other researchers argue the data is too noisy for a definitive conclusion. The TRAPPIST-1 system continues to be observed, with TRAPPIST-1e showing hints of a nitrogen-rich atmosphere, but Venus-like and Mars-like compositions cannot be ruled out. A sobering 2025 paper by Lunine and Seeger, published in the Proceedings of the National Academy of Sciences, confirmed what many suspected. Detecting biosignatures on true Earth analogues orbiting sun-like stars is far beyond JWST's capabilities. The contrast ratios are too extreme. The signal is too faint. The Habitable Worlds Observatory, a proposed next-generation space telescope, is at least 20 years away. We are building better eyes, but the universe we need to see is still just beyond our reach. Meanwhile, the Fermi Paradox itself is still generating new solutions, and some of them are strikingly different from anything proposed before. In 2025, Amedeo Balbi and Avi Lingam published what they called the mundane galaxy solution in the journal Astrobiology. Their argument is disarmingly simple. What if civilizations have a ceiling? What if there is a maximum level of technological development that no species ever exceeds, not because of catastrophe or extinction, but because of physics, economics, diminishing returns, thermodynamic limits? In this scenario, civilizations never build Dyson spheres because Dyson spheres are not practical. They never colonize the galaxy because interstellar colonization is not worth the energy cost. They exist, but they produce only leakage radiation, faint signals that dissipate into the noise of the cosmos within a few dozen light years. The universe is not empty. It is full of modest civilizations that never become spectacular enough to be visible. Latham Boyle at the Perimeter Institute proposed something even stranger in August 2024. What if advanced civilizations communicate using quantum channels, sending qubits instead of classical radio signals? Quantum communication is, by its nature, undetectable by anyone who is not the intended recipient. You cannot eavesdrop on a quantum channel without destroying the information it carries. If the galaxy is full of civilizations whispering to each other in quantum, our classical radio telescopes would hear nothing. The silence would not mean absence. It would mean that we are using the wrong kind of ear. These ideas, Balbi and Lingham's technological ceiling and Boyle's quantum communication, are important because they occupy different positions on the spectrum of explanations. The mundane galaxy says civilizations are there but quiet. Boyle says they are there and communicating but invisible to our instruments. The dark forest says they are there and hiding deliberately. Schroeder's artificial nature says they are there and invisible accidentally. The zoo hypothesis says they are there and watching but not talking. And the Planetarium Hypothesis says they are there and have built a machine to ensure we never find out. What is remarkable is that all of these explanations, every single one, accepts the same starting premise. The numbers say someone should be out there. The silence is the anomaly. The debate is only about what kind of silence it is. And there is a philosophical lineage to this debate that goes back far further than Fermi's lunch. More than 2,000 years further, in fact. In the Republic, written around 375 BCE, Plato described prisoners chained since birth inside a cave, seeing only shadows cast by a fire on a wall behind them. The shadows are their entire reality. They have names for the shadows, theories about the shadows, a complete understanding of a world that is, in every way that matters, a projection. Plato's point was epistemological. How would you know if your reality were a shadow of something deeper? The answer, Plato thought, was philosophy, the chained prisoner who breaks free and sees the fire. The real objects, the sunlight outside the cave, is the philosopher who perceives truth beyond appearances. René Descartes, in 1641, pushed this further with his genius malignus, his evil demon. What if there were a malicious entity powerful enough to fabricate an entire illusory world, deceiving you through all five senses? Descartes' purpose was to find something that could not be doubted even under this extreme scenario, and he arrived at the cogito. I think, therefore I am. You can doubt everything about the world, but you cannot doubt that there is a you doing the doubting. The Planetarium Hypothesis is, in a precise sense, a technological update of Descartes' evil demon. Replace the supernatural demon with a Type 3 civilization. Replace magical deception with information engineering. The structure of the doubt is identical. Hilary Putnam, in 1981, modernized the thought experiment further with his brain in a vat scenario. A brain floating in nutrient fluid, wired to a supercomputer that feeds it a perfect simulation of reality. Putnam's twist was to argue, using semantic externalism, that the scenario is self-refuting. A brain that has never existed outside the simulation cannot meaningfully refer to actual brains or actual vats. The words brain and vat in the simulated world refer to simulated brains and simulated vats. So the statement, "I am a brain in a vat," if uttered inside the simulation, is necessarily false. Bostrom sidesteps this argument entirely by making his case probabilistic rather than semantic. And Baxter sidesteps it by insisting that we are not brains in vats at all. We are real brains in a real world looking at a fake sky. The philosophical lineage matters because it shows that the question is not new. What is new is that it is beginning to acquire experimental answers. The newest theoretical work is where the ground is shifting most dramatically. In December 2025, David Wolpert at the Santa Fe Institute published the first mathematically precise framework for analyzing the simulation hypothesis in the Journal of Physics. Complexity. Wolpert's paper is significant because it treats the question with the kind of rigor usually reserved for physics, not philosophy. His findings are strange. Simulated universes can be as computationally powerful as their simulators, which means a simulation could itself run simulations, which could themselves run simulations in an infinite chain. There is no logical barrier to nesting, but more importantly for our purposes, Wolpert's framework provides tools for reasoning about what a simulated or manipulated universe would look like from the inside. In the opposite direction, a group led by Faisal, Krauss, Shabir, and Marino published a paper in June 2025 in the Journal of Holography Applications in Physics, claiming to have mathematically proven that the universe cannot be simulated. Their argument uses Gödel's incompleteness theorem, which states that any sufficiently powerful formal system contains truths it cannot prove. They argue that the mathematical structure of the universe is complex enough that no simulator could fully model it without running into Gödelian incompleteness barriers. The paper is provocative but has been met with significant skepticism, partly because it was published in a relatively new and less established journal, and partly because applying Gödel's theorem to physical systems is a move that makes many mathematicians uncomfortable. David Chalmers, probably the most famous living philosopher of mind, published Taking the Simulation Hypothesis Seriously in Philosophy and Phenomenological Research in 2024, alongside responses from Peter Godfrey Smith, Susan Schneider, and Eric Schwitzgiebel. Chalmers argues that even if we are in a simulation, the objects around us are still real in any meaningful sense of the word. A simulated apple is still an apple. It has the structure and function and causal properties of an apple. It just happens to be implemented in computation rather than in quarks. This argument has implications for the planetarium too. Even if the sky is a projection, the projection is still something. It has properties, structure, information, and information, as we have spent this entire video establishing, might be all that anything is. Then there is Vopson's proposed experiment, still unperformed as of early 2026, still published in AIP Advances rather than in Physical Review or Nature, still criticized by Sabine Hossenfelder and others, but still genuinely a proposed laboratory experiment whose result would bear directly on whether information is a physical substance with mass and energy. If you annihilate an electron and a positron, you get gamma rays. Vopson's prediction is that you would also get additional infrared photons at about 50 micrometers wavelength, carrying away the information content of the annihilated particles, roughly 1.5 bits per particle. If those photons are there, information is physical. If information is physical, reality is informational. And if reality is informational, then the distinction between real sky and projected sky becomes a question of data provenance, not metaphysics. I want to flag clearly that this experiment has not been done, that Vopson's theoretical framework has not been accepted by the physics mainstream, and that extraordinary claims require extraordinary evidence. But the fact that such an experiment can even be designed marks a change. 20 years ago, the simulation and planetarium questions were purely philosophical. 10 years ago, Bean, Davoudi, and Savage showed they had experimental handles. Today, multiple groups are developing specific, concrete tests whose results would constrain the space of possibilities. The conversation is migrating from philosophy to physics, slowly, tentatively, but detectably. There is one last piece of the puzzle that I have been holding back. It is the simplest, and in some ways, it is the most disturbing. The measurement problem in quantum mechanics is, depending on who you ask, either the deepest unsolved problem in physics or a non-problem that has already been solved by decoherence, and everyone just refuses to accept the answer. Here is the version that matters for this video. Quantum mechanics says that before a measurement is made, a particle does not have a definite state. It exists in a superposition, a combination of all possible states at once. When a measurement is performed, the superposition collapses into a single definite result. This is not controversial. Every physics experiment in the last 100 years confirms it. What is controversial is the question of what a measurement actually is and why it produces a definite result. There is an analogy that has become popular in simulation discourse, and I want to describe it and then explain why it is mostly wrong, because the correction is more interesting than the analogy. The analogy, quantum superposition, is like an unrendered scene in a video game. The game does not bother computing the textures and details of areas the player is not looking at. It only renders what the player sees. This saves computational resources. Measurement, in this analogy, is rendering. The universe does not bother deciding the state of a particle until something forces it to. This is computationally efficient. It is what a smart simulation would do. The analogy is seductive. It maps quantum weirdness onto computational logic in a way that feels intuitive. But it is mostly wrong, and the reason it is wrong is important. In quantum mechanics, measurement does not require a conscious observer. It does not require a human being. It does not require a physicist with a PhD, as John Bell sarcastically asked. Was the wave function waiting to jump for thousands of millions of years until a single-celled living creature appeared? Or did it have to wait a little longer for some highly qualified measurer with a PhD? No. Any physical interaction constitutes a measurement. When a photon bounces off an air molecule, that is a measurement. When a particle interacts with the thermal bath of the cosmic microwave background, that is a measurement. Decoherence, the physical process by which environmental interactions destroy quantum coherence, happens constantly, everywhere, to everything. It does not wait for someone to look. So the video game analogy fails, because the universe is not saving resources by keeping things unrendered until an observer looks. Things are rendered in the sense of having definite states all the time, by virtue of their constant interactions with their environment. The measurement problem is not about observers. It is about why the mathematics of quantum mechanics contains two different rules: the smooth, deterministic evolution of the wave function, Schrödinger's equation, and the abrupt, probabilistic collapse upon measurement, the Born rule, and whether these two rules can be unified into a single, deeper framework. But here is where the correction gets interesting. Even after decoherence, even after the wave function has effectively collapsed through environmental interaction, the measurement problem does not go away. It just changes form. The question is no longer, why does collapse happen? But why do we experience one outcome rather than the superposition of all outcomes that the Schrödinger equation predicts? Everett's many worlds interpretation says we do experience all outcomes in branching copies of ourselves. Copenhagen says one outcome is selected and the others vanish. Objective collapse theories say the wave function physically collapses via mechanisms we have not yet discovered. None of these interpretations has been proven. None has been ruled out. After a century of quantum mechanics, the deepest question about reality, the question of what happens when physics meets observation, remains open. And an open question, for the purposes of this video, is exactly what we want, because the Planetarium Hypothesis does not need the measurement problem to be evidence of simulation. It needs only this: the fundamental nature of reality at the deepest level we can currently probe is stranger and more information-centric than anyone expected 100 years ago. The universe behaves in certain specific and measurable ways, as though information is more fundamental than matter. Whether that is because the universe is a computation, because it is a holographic projection, because information is woven into the fabric of space-time at a level deeper than our current theories reach, or because there is a Type 3 civilization running a planetarium projector at the edge of our solar system, remains an open question. And it may remain open for a long time, I want to return to where we started, not to the Planetarium Hypothesis itself, to the people. Enrico Fermi asked his question in the summer of 1950 and died 4 years later without hearing an answer. Frank Drake spent 62 years listening and died in 2022 without hearing one either. Jill Tarter is still listening. She has spent more than half a century waiting for a signal that may be hidden behind a dome she cannot see. John Wheeler asked his mother, as a small boy in a bathtub, "What happens when you get to the end of things?" He spent 80 years answering that question. He named black holes, coined wormholes, supervised 46 doctoral students, worked with both Einstein and Bohr, and at 78 proposed that reality is made of information. He died at 96, in 2008, having pushed the boundary of human understanding further than almost any physicist who ever lived. But he never stopped grieving his brother. Joe Wheeler, the historian turned army officer, who sent a 2-word postcard from Italy saying, "Hurry up," and was killed in combat on October 25, 1944. Wheeler carried that loss for 64 years. He wept about it as an old man. A colleague recalled that Wheeler had all but cried when calculations showed that Einstein's theory ruled out wormhole travel, and the colleague believed it was because Wheeler had been hoping, somewhere beneath the equations, to find a way back to the brother he lost. And here is the connection that runs through this entire story, like a wire. Wheeler proposed that reality is made of information, that the universe is not a collection of things, but a web of questions and answers, bits and measurements, observations that create the reality they observe. If he is right, then the night sky is not a thing. It is a message. It is information arriving at our instruments and being decoded into a picture of the cosmos. And if the sky is a message, then the question the Planetarium Hypothesis asks is the simplest question you can ask about any message. Is it true? We do not know. 75 years after Fermi's lunch, after 6 decades of SETI, after Kepler and Hubble and Webb and Planck, after the discovery of 6,000 exoplanets and 300 million potentially habitable worlds, the universe remains silent. The silence is consistent with emptiness, but it is also consistent with concealment. And distinguishing between the two may be the defining scientific challenge of the next century. The physics is giving us tools. The holographic principle tells us that 3-dimensional reality may be encoded on a 2-dimensional surface, which means the sky is already, in some sense, a projection. Bekenstein's bound tells us the universe contains finite information, which means it is, in principle, computable. Cosmic ray experiments constrain the fineness of any lattice structure in spacetime. CMB anomalies reveal features in the oldest light that nobody can fully explain. Dyson sphere candidates show infrared excesses around nearby stars that nobody can yet attribute to natural causes, and proposed experiments, if they are ever conducted, could detect whether information itself has physical mass. None of this proves we are inside a planetarium. None of it disproves it either. What it does is something more subtle and more important. It converts the question from philosophy into physics. It moves the boundary between what we can speculate about and what we can, in principle, test. Baxter calculated that the dome would crack if humanity expanded to span 100 light years. We are currently confined to a single planet. We have not yet left the solar system. Voyager 1, the most distant human-made object, is roughly 163 astronomical units from Earth. That is about 0.0026 light-years. We are nowhere close to 100 light-years. We are infants in a crib, and the dome, if it exists, has nothing to worry about. But we are building better telescopes. We are developing quantum computers that might one day simulate the physics of the early universe. We are designing experiments that test whether information is a substance, whether space-time has structure, whether the deepest features of reality are consistent with being natural, or whether they bear the fingerprints of engineering. If the planetarium is real, it was built to contain a species that stays small. Every telescope we build, every experiment we design, every probe we send deeper into space is a stress test of the dome. And the dome was built with a known failure point. Wheeler asked, "As a boy, what happens when you get to the end of things?" We do not know yet, but we are getting closer to the edge. And whatever is on the other side, whether it is more universe or the machinery of deception or something we have not imagined, the asking is what makes us human. Wheeler understood this. He built his entire career on the principle that the right question, asked with enough precision, does not just reveal reality, it creates it. We are asking. The sky, whatever it is listening.